Okay, so this section we're going to be graphing quadratics in Vertex form. Make sure you take time to pause, get everything copied down in your notes. Make sure you guys get everything written down and maybe even go back and watch it and listen to the things that I say as I work through some of these problems, because some of that helps. So first thing we're going to do is pretty simple. We're going to learn how to identify the difference between even and odd functions. And then we're going to kind of break apart vertex form into what it does. So being able to graph our quadratics when it's a and h, and then when it's a, h, and k. So the first thing, again, you guys can pause and write this all down, but really you don't need to write everything down. What you need to understand is when a function is even, if I were to plug in negative x in for my input, so my function evaluated at negative x, my answer, when I plug in a negative sign, should look exactly like the original function if it's even. However, if my function is odd, when I go to plug in that negative sign, everything will change. So when that negative sign is in front, that means every term in my function will change signs. And if it doesn't do either, or changes half and half, the function is just said to be neither even nor odd. So in the first example, if I were to plug negative x in, it would look like this. And if I were to evaluate, my function evaluated at negative x is equal to negative 2x, because 2 times negative x is negative 2x. So if I look up at my patterns, that would be an odd function because it changed so that every term, or in this case just that one term, was negative. So this function is odd. Okay, if I do the same thing here, and this function's name is g, so let's label that properly. G of negative x is equal to negative x squared minus 2. If I take a negative times a negative, it's still just going to be positive x. So g evaluated at negative x is actually equal to g evaluated at positive x. So because those did not change, this function is even. Last one here, h. So we plug it in. When I evaluate here, the 2 times x squared stays positive, but my second term changes signs, and my negative 2 stays the same. So it can't be even or odd because it didn't stay the same, but it also didn't change all the way through. So this one is neither. Okay, so again, you're going to do the same thing here on this function. See if when you plug in a negative sign, if it's going to be even, odd, or neither. I'll go quickly here, so make sure you pause the video and try first. So here on this one, my function evaluated at negative x is going to be negative 5x. This function is going to be odd. G of x evaluated at negative x is equal to 2 to the negative x power. And as you'll recall, 2 to the negative x power just means 1 over 2 to the x power. This one's actually neither. Okay, I wouldn't expect you guys to have known that, but because it didn't change signs, it just did the reciprocal, it's neither. Okay, and then our last one here. Does not change. This function's even. Okay, so again, that helps you with even, odd, or neither. All right, so now kind of getting into this. Again, I would not necessarily write all this stuff down because it gets a little bit confusing as to what you're supposed to do. So what I want to draw your attention to is kind of the important parts. Right here it says if h is less than 0, it moves your function to the left. If h is greater than 0, it moves your function to the right. But what I want to draw your attention to is this right here. It has a negative sign in the function before h. So technically, when h is negative, you are going to see something that looks like this. My value here that I plugged in is -3, because when I write in vertex form, there's an implied negative that's already there. So when I see a plus sign, it's actually going to move your function left. When you see a minus sign, it's actually going to move your function right. The value of h is still -3, but what we see when we look at our function is that plus. So it's always kind of the opposite when you're working with your input and inside the parentheses there. Okay, so kind of in summary, if you see x plus the number, it's going to move it left. If you see x minus the number, it's going to move it right. So in this one, if I were to look at this and try to figure out what the value of h is here, it says x minus 4. So the value of h, my axis of symmetry, is actually +4. Now, just like before, when we found our axis of symmetry, first of all, we plugged it into our tables, or our values in the fill in the blank. But then what we would do, if we wanted to find our vertex, is we have to plug that value 4 into our function. So I'm going to show the work here. So we have our function g evaluated at 4 is equal to 1/2 times 4 minus 4 squared. When I plug that in, 4 minus 4 squared is 0 squared, and 0 squared is 0, so 0 times 1/2 is still equal to 0. Okay, so 1/2 times 0 is still 0. So our vertex here is at 4, 0. So now we would plot that. Now, before we go plugging in points, our transformations, you can answer this first or plug in some more points. But what we need to understand is that there is more work to do to find at least one other point. So our transformations, if we look at A is a vertical shrink. Okay, it's a vertical shrink by a factor of 1/2. And then our h value here is -4, but that actually moves it right 4. So those are the transformations from my parent graph. Now, if I want to find another coordinate point, I need to plug in a value that's close to my axis of symmetry. So my first value is 4. I'm going to plug in 3. When I plug 3 into my function, I have 1/2 times 3 minus 4 quantity squared. So that gives me 1/2 times -1 quantity squared, which is 1/2 times 1, which is just equal to 1/2. So at 3, I'm at 1/2. That means if I reflect across the x-axis, or excuse me, not the x-axis, but the axis of symmetry, 1 unit to the right of 3 is going to be 5, 1/2. So I'll plot that right there. Next closest value is 2, so I'm going to plug in 2. Function evaluated at 2 is 1/2 times 2 minus 4 squared. 2 minus 4 squared is 2, so I have -2 squared. 1/2 times -2 squared is 4, and 1/2 of 4 is 2. So at 2, my output is at 2. Which means if I reflect across 4 at 6, my output should also be 2. And there we have our graph. Now, domain is always easy. Domain is always all reals. My range here, I want to look at the y value always of my vertex. And because my function is opening up, its y is greater than or equal to 0. Again, this stuff right here is absolutely pivotal, that we find a second and third point and reflect them. So on this one, again, when we go to work these out, it should be pretty easy to identify our axis of symmetry. So on the first one, our axis of symmetry, and again, pause and try these, but our first one, our axis of symmetry is at -5. If I plug in -5, I'm going to end up with 0 again, so my vertex is going to be at -5, 0. So axis of symmetry is -5, and I get -5, 0 when I plug it in. Now, if I plug in a point 1, excuse me, not 1, I don't want to plug in 1, I want to plug in 4, -4, geez. So if I plug in -4, I have 2 times -4 plus 5 squared, which is 2 times 1 squared, which is just 2. So if I plug in -4, I get 2, and then I can use the reflection. The next closest point is 3, so 2 times -3 plus 5 squared, 2 times 2 squared, and 2 squared is 4 times 2 is 8. So at -3, my function is already all the way up at 8, and we plot its reflection at -7. So here's our function. You can see the transformations here. We have a vertical stretch by a factor of 2, and we moved our function left 5. Okay, we have 2 transformations. Our domain is all reals. Our range is y is greater than or equal to 0 again. Our axis of symmetry on the next one, because it's -2, is actually going to be +2. When we plug in 2, we're going to still get 0. So our axis of symmetry is equal to 2. We're going to get 2, 0. Our transformations, there's no stretch or shrink, but there is, because of that negative sign, an x reflection. And again, we moved right 2. So now when I go to plug in points like not -1, but 1, if I plug in 1, -2 squared, 1 minus 2 is -1, and I square it. Now, when I square -1, it's 1, but there's still a negative sign out in front. So at 1, I'm at -1, and at 3, I'm at -1. If I plug in 0, I have 0 minus 2 squared. There's a negative sign out in front, so -2 squared is 4. But again, there's still that negative sign out in front. So at 0, I'm at -4, and I plot the reflection. And there they go. Again, domain is all reals. Range is y. Instead of greater than or equal to this time, y is going to be less than or equal to 0 because that a value made it open down. Okay, so now we're going to throw k in the mix. Here's why it's called vertex form. The h and the k are going to tell you your vertex. So that's what the videos are saying right here. My h is still going to move it left and right. My k is going to move it up and down. But that should give me exactly what I want for my vertex when I go to plug in my points. We're going to start with our axis of symmetry by looking at h, and we can just plot our vertex by looking at k. We don't have to plug it in anymore. That's why vertex form's kind of nice. So on this one, our axis of symmetry, just by looking at the function, is x is equal to -2. Then we use that value, -2, and again, we don't need to plug it in because we know our output is going to be this value, k, right here, 3. So I can plot those things, -2, 3, so -2 is my axis of symmetry, 3 is my vertex. Now, here's where I need my transformations. If I look at all these things, and we'll color them down the line, negative sign gives me an x reflection. Okay, let's go green. The 2 gives me a vertical stretch. Okay, the 2 inside will go purple. This 2 right here, moved it left 2. And the 3 on the back end there will go in red. Moved it up 3. So there's a lot of transformations in just this one problem. Again, we can plug in a point next to our axis of symmetry. So let's plug in -1. So -2, whoops, and then -1 plus 2 quantity squared plus 3. So -2, -1 plus 2 is 1 squared plus 3. 1 squared is 1 times -2 is just -2 plus 3. And we get, when we plug in -1, we get 1 for our output. So we plot that, -1 comma 1, and then we use our reflection. So at -3, it's also 1. Okay, we can plug in our next closest point, which happens to be 0. So 0 plus 2 squared plus 3. So we have 2 squared plus 3. 2 squared is 4, so 2 times 4 is going to be -8 plus 3. And we get -5. So at 0, we're at -5. And then our reflection at -4, -5. So we always want to utilize those reflections to our advantage. Our domain, again, pretty self-explanatory. It's all reals all the time. We can plug in whatever we want. Our range here is y is less than or equal to, because my function opened down, and we get 3 for our vertex there. Okay, but vertex form should always be kind of a shortcut. Okay. Now, transforming a graph is no different than what we saw in the previous lesson. When you see something like this, it depends on where this term is. So if it says x plus 5 inside the parentheses, you are going to change your h. Okay, but if it says x plus 5 like this, and that 5 is outside, you are going to change your k. Okay, and lastly, if it says something like this, that's where you are going to change. Actually, you're going to end up changing the a and the k. You're going to multiply that 3 by the a and the k that's on the outside. So those will be a little different. I know I have axis of symmetry and all that stuff there, but I just want you to take into consideration, again, just for the sake of time on the video, I'm going to show you this example, and then I'll upload the completed notes so you can see the work done for these on Canvas for you. So I'm going to finish out this example here. So it was plus 5 on our previous function, and our previous function, I'm going to write it up here and then drag it down actually. So here's our previous function. We have g of x is equal to -2 x plus 2 squared plus 3. Okay, so I'm going to lasso this and drag this down here. Okay, so what it wants us to do for our new function f is it wants us to add 5 to that h value. So f of x is equal to -2 x plus 2, and then we need to add 5 squared plus 3. So now we can just simplify this and we'll be done. So -2 x plus 7 squared plus 3. Now, in terms of what transformation it did, it moved my function left 5 units. Okay, so there's our practice problems worked out. There's the lesson worked out. And again, we're to the summary page minus the ones that you guys should try and practice right here. I'm going to work these out, post them to Canvas. Make sure you guys go check that out. Okay, rewatch the video, listen to the things that I say once you copy the notes down, and make sure you understand what's going on and what I'm saying as I work the problems out. Thank you guys. Have a great day.